Okay, so in this next video, we're going to talk about some radicals. And radicals, we're talking about square roots, basically. So I want to start with just a quick reminder of the difference between rational numbers and irrational. Now, rational has this word ratio in it, which means I can write it as a fraction, but it's probably easier to tell the difference between rational and irrational when we write it as a decimal. Okay. When a rational number is written as a decimal, it's going to end, for example, 0.2, or it's going to repeat with some sort of a pattern, like 0.1515. An irrational number, on the other hand, if I write it as a decimal, it's going to just continue infinitely with no pattern at all. Okay, a good example of this would be pi. Okay, so this is the difference if we're looking at the numbers between rational and irrational. Now, when we're talking about square roots are the opposite or the inverse of a square. Okay, so the square root symbol looks like this, the radical symbol. And if I want to know the difference between rational and irrational for them, well, a rational number is going to have a perfect square inside the radical. Okay? And there's actually a name for what's inside the radical. We call it the radicand. Okay? So the radicand is just everything underneath the radical symbol. If that's a perfect square, then my number is rational. If it's not a perfect square, then it's irrational. To multiply and divide square roots, multiplying pretty easy. If I've got two separate radicals and I want to multiply them, I can just multiply the radicands and leave that product underneath the radical. Okay? With dividing, it's a little bit more complicated. If you're lucky, the denominator inside the radical will divide evenly into the numerator, in which case we can just simplify it. If not, though, we have to do a process called rationalizing, which means I need to get the radical out of the denominator. When this is a monomial, we do that just by multiplying by the radical in the denominator. What I get as a result is we get the product of the two radicals from the numerator, and then the denominator, rad b times rad b, is just b. And this is kind of a cool result that's always going to be true. If I have the product of two radicals that are the same, okay, well, when I multiply something by itself, that's squaring it. And squaring and taking a square root are inverses of one another. They cancel each other out. So if I ever multiply a square root times itself, I just get the result of that number that was under the square root, the radicand. Okay, so in this particular problem, I have 1/2 times our radicand 2 after we square it, and so my total result is 1. In example B, I just have a product of two radicands, so I can multiply them, we get 36, and the square root of 36 we know is just 6. Moving right along, in example C, we are fortunate enough that 5 does divide into 125 evenly. So because these two things are both under the square root, I can divide them one into the other. So 125 divided by 5 is 25, and the square root of 25 is 5. Finally, in example D, I just want to be careful that I don't mix up things that are inside the radical with things that are outside. So things that are inside the radical, I can divide them. 98 divided by 2 is going to give me 49. And things outside the radical, I can divide them as well. So 16 divided by 4 gives me a 4. Okay, so we just want to make sure that we're keeping those things separate. And then to finish up, the square root of 49, it's a perfect square. Square root of 49 is 7. So I have 4 times 7, which is 28. Okay. Moving along. When I want to simplify square roots, okay, if I don't have a perfect square on the inside, I want to make sure that I don't leave any perfect square factors. I want to pull all of those out. So if I want to separate, for example, 75 into a perfect square factor and a not perfect square, well, I can split 75 into 25 times 3. Okay. 25 is a perfect square. Square root of 25 is 5. And the rad 3 is going to have to stay inside the radical. If there's no perfect square factor, it's got to stay inside. Okay, can't come out. Now in example B, I want to show you kind of another method. Not really another method, but just something that might happen. Okay. The square root of 80, you might see the square root of 80 and say, okay, well 80, I know I can split into 4 times 20, right? 4 times 20, and 4 is a perfect square. So I can write this then as 2 times the square root of 20. Okay. Now this is nice because I can cancel out that 2 with the original 2 from the denominator. And so I'm left with the square root of 20. The problem here is that I'm not finished. You're never ever finished until you've gotten rid of all of those perfect squares. And 20 can be split into another perfect square, 4 times 5. So I want to make sure that I simplify all the way. So this is going to reduce totally to 2 times the square root of 5. 2 because that's the square root of 4. So just make sure if you're simplifying that you go all the way to the end, that the thing left in the radical at the end doesn't have any perfect square factors. Okay? But just keep in mind also that this could have been shorter had we found a larger perfect square at the beginning. Square root of 80, for example, 80 can be split also into 16 times 5, and we would have gotten 4 rad 5 to begin with. Okay? And then divided by 2 would have given me that 2 rad 5. So if we find the larger perfect squares to begin with, then you'll have an easier time. You'll be able to do this in shorter steps. Okay? Now, next rule, I want to make sure that I never leave a fraction inside of a radical. We always want to simplify those fractions. Now, two ways that we can address this. One is I can actually split up a radical so that there are separate radicals for the top and bottom of my fraction. Okay, in this problem, this is what I want to do because the denominator, square root of 64, is a rational number. That's 8. Okay. And so now I don't have any more radical in the denominator, I don't have any more fraction inside the radical, and so we're done. Our other option, in example B, I see a square root of 90 tenths. Now, this one's also pretty nice because 90 tenths can be reduced. 10 goes into 99 times, so I have the square root of 9, which is just 3. Okay. Now, I don't, though, want to leave any kind of fraction in the denominator, any kind of radical in the denominator. So, if example A, for example, we have to do that process that we saw on the earlier page when we were talking about the rules. I want to rationalize, so I multiply by that square root on the top and bottom, square root of 5, top and bottom. And so I'm going to have 3 times the square root of 5 on the top. And then rad 5 times rad 5 is the square root of 25, or just 5 in the denominator. Okay, and this is my result. And notice, I'm not going to simplify the 5's on the top and bottom because one's inside the radical and one's outside. There's nothing I can do about that. Now, I could try to do kind of the same thing in this problem, but you should see we're going to run into some issues if I try to do that. Because if I try to multiply this rad 13 in the denominator, well, here that will rationalize and I'll lose the radical, but I would have to distribute it in here, and so we wouldn't actually get rid of the radical in the denominator. So instead, I'm going to do what's called multiplying by a conjugate. Okay? The conjugate, if you remember, is the same two terms, but a different sign in between. So I'm going to multiply by, instead of 7 plus rad 13, 7 minus rad 13 on the top and bottom. 7 minus rad 13. Okay. So on the top, I can distribute the 9 into this binomial here. So 9 times 7 is 63, and then minus 9 times the square root of 13. Okay, so that's my numerator. Denominator, I've got a binomial times a binomial I FOIL, so 7 times 7 is 49. Now what happens with the conjugates when I multiply them, 7 times negative rad 13 is negative 7 rad 13, and then positive rad 13 times 7 is positive 7 rad 13. So these two terms in the middle are going to cancel each other out. That's why we want to multiply by the radical, by the conjugate. Okay. And then finally in the last term, positive rad 13 times negative rad 13, well, a positive times a negative is a negative, and rad 13 times rad 13 is just 13. Okay. So now, because I've multiplied by that conjugate, all of my rads are out of the denominator. So I just have my 63 minus 9 rad 13 on the top, and on the bottom we've got 49 minus 13, which is 36. Okay, the last thing I want to do is just double check and see if I can reduce this. So I'm looking at my 3 factors, 3 terms, and I want to see if they have a common factor. They do have a common factor of 4, so I can reduce, of 9. I can reduce everything by a factor of 9. So 63 divided by 9 gives me 7 minus just a rad 13 over 4. Okay. Make sure you do simplify that at the end. So that's multiplying and dividing. When I add and subtract square roots, I want to make sure that I'm adding and subtracting like terms, like radicals. And for me, that's going to mean that they have the same radicand. So for example, in part A, it looks like I can't add them because I don't have the same thing under the radicand. But I can see if I can maybe simplify this. Rad 40, I know, is 4 times 10. So this is going to reduce to 2 rad 10. And rad 90, well, that's 9 times 10, so that can reduce to 3 rad 10. Okay. So when I multiply, I've got 8 rad 10 plus 15 rad 10. And now these are like terms. They both have that rad 10. So we've got 23. We add the coefficients. Rad 10 as my final answer here. Similarly, in this next problem, 7 rad 300. Well, rad 300, I can multiply 100 times 3. So that's going to give me 10 rad 3. And then 5 times 27 is 9 times 3. So this is 3 rad 3. Multiply times those coefficients. So we've got 70 rad 3 minus 15 rad 3. And that's going to give me 55 rad 3 altogether. Okay, so I do get those like terms, and then I can add or subtract. In example C, I just want to multiply, but I've got a binomial times a binomial, so we are going to have to FOIL here. So 8 times 5 gives me 40. Outside's 8 times negative rad 7, so negative 8 rad 7. Inside's, this is 5 rad 7. And then the last, positive times negative is negative. Rad 7 times rad 7 is 7. So combining our like terms, I've got 40 minus 7 gives me 33. And then negative 8 rad 7 plus 5 rad 7 is going to be negative 3 rad 7. Okay, so there's some operations with radicals. The last thing about radicals I want to talk about is a special use for them, which is the Pythagorean theorem. So Pythagorean theorem, we should remember, is a squared plus b squared equals c squared. Okay, and this is going to relate the lengths of right triangles, the lengths of the three sides. Now the thing we want to keep in mind when we're talking about a squared, b squared, and c squared, a and b doesn't matter so much, they're both legs, but c must always be the hypotenuse, and hypotenuse of course meaning the side across from the right angle. So in the example A here, I'm looking for this third side, which is the hypotenuse, and that makes x c. So I'm going to have 6 squared plus 3 squared equals x squared. And we're just going to solve for x here. So this is 36 plus 9. Okay, 36 and 9 gives me 45. And to solve for x, I'm going to square root both sides. Okay, now the square root of 45, 45 is 9 times 5. So that's going to give me 3 rad 5 to simplify. Okay, so that's the length of that missing third side. Now in B, this one's my right angle here, if you couldn't tell. Okay, and so now I notice the thing that I'm missing is not the hypotenuse, because the hypotenuse is down here. Okay, so 13 is the hypotenuse. So I'm going to write this way. 5 squared plus x squared is equal to 13 squared, and we simplify this. So we've got 25 plus x squared is equal to 169. And we're going to solve for x here. So I subtract 25. X squared is equal to 144. And when I square root here, x is equal to 12. Okay, so that's some radicals and some applications of radicals.